Hello everyone, I am here to provide a review of MAE213 course topics for the purpose of helping you with the for the final exam. I wanted to say though that this has nothing to do with the problems that are going to be on the final exam because I haven't seen the problems yet, but this is just to help you remind what topics we have covered in this course. Okay. So at the very beginning of the course we discussed the equilibrium of deformable bodies, and the same equations of equilibrium can be applied to rigid bodies as well as deformable bodies. Then we talked about internal loadings. So those are loadings between fibers inside of deformable bodies. And in general, we could use the method of sections to determine internal loadings. The method of sections is the most important method that we have introduced in this course this semester. The idea is that you can use a plane to cut the deformable body into two parts. Then you can draw a free body diagram of either of the two parts, and you would include internal loadings on the cut section as well as any externally applied loadings on that part of the body. So if this is a body and you can make a cut any way you want using a plane passing through the body, then your free body diagram could be either the first half of the body or the second half of the body. They are equivalent. Okay? For 2D problems, in general, on this cut section we have different types of internal loadings. We could have a normal force that is normal to the cut section. We can have a shear force that is tangential to the cut section. We could have a bending moment. We could also have a torque. And the most important thing to note here is that you should only include externally applied loadings that are actually applied on this part of the body. So when there is a distributed load that is, for example, applied to the body like this, and if this is your cut, and you choose to draw a free body diagram of the left portion or the right portion, then you only include the distributed load that is applied actually on this segment of the entire body, not all of it. Okay, so that's a very important thing to note when you use method of sections. So that's the first important topic for this course. Then we started to introduce a concept of stress. So definition of stress. So stress is defined to be the intensity of internal loadings, and it is force per unit area. Internal loading divided by area. So in general, there are two types of stresses. Normal stress and shear stress. So if we look at a cut section, if there is a normal force N and a shear force V, then the normal stress is defined to be N divided by the area on which this internal normal force is acting on. And then the shear force is tau, that is due to the shear stress is tau, and that is due to the shear force V. Okay. So normal is normal to a section, shear is tangential to a section. Now shear stresses are seen on cross sections of nuts and bolts connectors, pins, and we've introduced the concept of double shear and single shear. When a pin is used or a bolt is used to connect three members, then we have double shear. Otherwise, if a pin is used to connect two members, then we have single shear. I won't go into the details of how the formula was derived, but for single shear, you can directly use the force that's acting on the pin or the bolt divided by the cross-sectional area of the pin or the bolt. And for double shear, we could use F divided by 2 and then divided by the cross-sectional area of the boat. Here again, F is a force that is acting on a pin or a boat. So that's the definition of stress, and stress has the units of force per unit length squared. Alright, so this is the second topic. The third one is definition of strain. There are two types of strains, normal strain and shear strain. Normal strain has a symbol of epsilon, and shear strain is denoted by gamma. So normal strain characterizes the dimensionless change of length of a line segment in a body per unit original length. So it is defined as the new length after deformation of a line segment subtracted by the original length divided by the original length. In other words, it is change of length per unit original length. And this change of length sometimes is denoted using a single delta. So change of length per unit original length. That is normal strain. It is a dimensionless quantity because we have length over length. So don't confuse a change of length with strain. Okay, there are different quantities. One of them is in terms of length, the other one is dimensionless. Shear strain is defined as change of angle between two line segments that were originally 90 degrees apart from each other before deformation. So this is the original angle minus the new angle. If we sketch it, so we originally have two line segments that have an angle of pi over 2 between them. This is before deformation. And after deformation, these lines might deform to something like this. And then we measure the new angle between them as theta. So the difference is defined to be gamma. Okay. Now this has units of radian, which is again dimensionless. The radians are considered to be dimensionless, but it is in terms of an angle change. So both stress and strain can be either positive or negative. When we have a positive stress, we say that we have a tensile stress. Otherwise, when the stress turns out to be negative, we say that we have a compressive stress. Same here, when we have a positive epsilon, positive normal strain, then we say that the line segment has been elongated. Otherwise, if it is negative, then the line segment has been contracted. Okay? For shear strain, if it is positive, that just means that after deformation, the angle between the two line segments becomes smaller than pi over 2. Otherwise, if gamma is smaller than 0, when we have a negative gamma, then that means that the angle after deformation becomes larger than pi over 2. So this is the definition of strain. And then after this, we discussed the relationship between strain and stress, and we introduced different material properties. So stress-strain relationships. So we could sketch from experiments like the simple tension test or simple compression test. We could sketch the stress-strain diagram, and we have a version for the normal stress and normal strain. We also have a version for the shear stress and shear strain. Now for ductile materials and brittle materials, the stress-strain diagrams look different. For ductile materials, most of the stress-strain diagrams look like this. You would have a linear portion, and then a little flat portion, and then the curve keeps going up and then down, something like this. Okay. Now for different materials, the actual stress-strain diagrams may look different than this version, but in general, there are different regions like this one. Similarly, for the shear stress-strain diagram, For ductile materials, it looks something like this. So there is a linear portion, and when the material's stress and strain are in the linear portion, we say that the material is linear elastic. When that is the case, the stress and strain are related to each other linearly through what we call Hooke's law. Okay. And E and G are material properties. Those are also the slopes of the linear portion on these diagrams. So E is the elastic modulus of a material, also known as the Young's modulus. And G is the shear modulus of the material. Now for brittle materials, the diagram normally looks like something like this. Okay, there's not a clear linear portion, and there's not a up and down feature on the diagram. So basically, the material fails very abruptly and suddenly, and it's called brittle fracture. Okay. Now on this diagram, there are some important points. For example, we have the yield stress, which is the stress at which the material starts to yield, and that is only for ductile materials. So yielding is considered to be a mode of failure for ductile materials. Okay, when yielding starts to occur, we consider that the material has already failed. We also have brittle fracture. At that point, we have what we call the fracture stress. So stresses like the yield stress and the fracture stress are both considered to be stress when the material is at failure. Okay, so those are the different relationships. Then we have also introduced the Poisson's effect and the Poisson's ratio, which is another material property. So the Poisson's effect refers to when you have a bar, for example, which has a longitudinal direction, in this case as the horizontal direction, and if it is being pulled, we know that there will be elongation along the longitudinal axis. And when the bar is elongated, there will be contraction in this vertical direction. So its cross-sectional dimensions will decrease, okay, because of that. So the deformed shape might look like this. So the bar would become a little longer, but also thinner in the cross-sectional dimension. So this is called the Poisson's effect. And again, this is considered to be the longitudinal direction, and we have two lateral directions. So the directions that are perpendicular to the longitudinal direction, those are considered to be the lateral directions. The strain, the normal strain, which again is used to characterize the change of dimension in each of these two directions, the normal strain epsilon, those two are related in the following way. We have, the Poisson's ratio mu defined as negative epsilon in the lateral direction divided by epsilon in the longitudinal direction. So change in dimensions in the lateral direction, in this case, if I call the longitudinal direction x, then we have either y or z to be the lateral direction. So the change of dimensions in either y or the z directions, that's defined as epsilon lateral. And epsilon longitudinal is the dimensionless change of length in the x direction. All right. These two are related, and there is a negative sign in this formula. That is because whenever we have elongation in one direction, we have contraction in the other. So the sign of these two epsilons are always opposite to each other. If epsilon longitudinal is positive, then epsilon lateral will be negative, vice versa. Therefore, we define Poisson's ratio to include a negative sign in the formula such that the Poisson's ratio will always be positive. So Poisson's ratio is another material property, and it is normally smaller or equal to 0.5. When it is 0.5, the material is considered to be incompressive. We're not going to go to the details of that, but just so that you know. And these three material properties, E, G, and nu, those are related in the following way. So E equals 2 times G times 1 plus nu. So out of these three, only 2 of those 3 material properties are independent material properties. Once you know 2 of the 3, you could always use this relationship to obtain the third one. So that's some discussions about material properties and stress-strain relationships. Then after all of these basics that we have introduced in this course, we started to look at 3 different types of problems, or applications I should say. We introduced the axially loaded members, torque loaded members, torsion problems, as well as beams. So next I will talk about all 3 of them in parallel with each other to show you comparisons and similarities. So let me create a table. So we have axially loaded members. We have torque loaded members. Again, these problems are referred to as torsion problems. And finally, we have beams. So let's first take a look at the types of loadings for each of these 3 cases. What type of loads are applied? Now for axially loaded members, we are looking at forces that are applied in a direction that's parallel to the longitudinal axis of the member. So we could have something like this. Forces applied to a member. We could have members that have changing cross sections. And we could have forces applied along the longitudinal axis of the member. We could have distributed axial forces applied. We could also have members that have changing cross-sectional areas. Okay. So that's for axially loaded members. Now for torque loaded members, the loads are torques. Now for torques, sometimes we use a little curved arrow to show the direction. It's clockwise or counterclockwise. Otherwise, sometimes we use 2 arrows to show that it is a torque. So the direction of the torque is determined using right-hand rule. So if we do use a curved arrow, then your fingers of your right hand are in the direction of the curved arrow, and then when you open up your thumb, that's the direction of the 2 arrows. So we have torques applied. Again, we could have cases where we have changing cross-sectional dimensions along the lanes of the member, or we could have continuous change of the cross-sectional dimensions. So that's torque-loaded members. Now for beams, the loads are applied in the direction that is perpendicular to the longitudinal axis of the member. Beams are long and slender members. So we could have forces applied, could be either distributed or concentrated, but those are perpendicular to the longitudinal axis. We could also have bending moments applied. Now the difference between a torque and a bending moment is that if you use right-hand rule, again, your fingers are in the direction of the curve, and then you open your thumb. If the thumb is in the direction that is perpendicular to the longitudinal axis of the member, then that's a bending moment. It's going to cause the member to bend. Otherwise, again, if the thumb using right-hand rule is in the direction of the longitudinal axis of the member, then you're creating a twist. That's when you have a torque. Okay. So these are the different types of loads on these different types of members. Next, let's take a look at the internal loadings that are found on cross sections of these members. So for axially loaded members, the internal loadings that we're looking at would be normal forces that are perpendicular to cross sections of the members. Those are also referred to as the axial forces. So when you use method of sections, you could make a cut along a specific cross section of interest, and then you could look at the internal normal force. Now there is a sign convention. When the normal force is pulling the cut section, then we say that the normal force is positive and the member is in tension. Otherwise, when it is pushing the cut section, then we say that it is negative and the member is being compressed or contracted. Okay, so we have an internal normal load or axial load. Now for torque-loaded members, the internal load is a torque. All right, so it's a torque. Again, there is a sign convention. When your thumb is in the direction that aligns with the outward normal of the cut section, then you have a positive torque. Otherwise, if the two arrows are pointing into the cut section, then you have a negative torque. It doesn't matter after you make a cut which side you're drawing your free body diagram with. It's always positive if it is pointing away from the cut section. That's a sign convention. Now for beams, there are two, in general, there are two internal loadings that we look at. We have a shear force, V, and a bending moment, M. Now the shear force is defined to be positive downward when you look at the cut section from the right-hand side. Bending moment is positive counterclockwise when you look at it from this side. Now from the other side, V is positive upward and M is positive in the clockwise direction. Okay. Now to obtain the internal loadings for these three types of cases, it's always important that we use method of sections and we make cuts. Now, sometimes we have to make a few cuts depending on how many segments of the bar we have or the member that we have. For example, in this case, the loads are applied at the very ends of the bar. Then we do not need to divide it into segments. We just have one segment and N is the same everywhere. You can verify this by drawing free body diagrams and by making different cuts along the length of the member. However, when this is the case, when you have multiple loads applied along the axis of the member, then you'd have to divide the beam into 1, 2, 3 segments in this case, because whenever there is a load applied, there is a change in internal normal force on the cross section right just to the left of this point and just to the right of the point. So in that case, you have to do method of sections 1, 2, 3 times, each time for one segment of the bar. So method of sections is very important. And once we do that, normally we draw what we call the internal load diagram. So you label the units on the axis and you draw how the internal normal force changes along the length of the member. For this case, same here, you can draw a diagram to show how the internal torques change along the length of a torque-loaded member. It could be positive or negative, etc. Now sometimes these are constant for each segment of the bar. Sometimes it could vary if you have distributed axial loads and distributed torques applied. Okay. And for beams, we draw what we call the shear and moment diagrams. Again, we have units and units labeled. Now this could be created using two different methods. We could either use the method of sections or we could use the graphical method. For the method of sections, same here, you would divide the beam into a few segments. So the division points are wherever you have a load applied, either a point load or a bending moment, or where you start to apply a distributed load, or where it ends. So in this case, you would have to divide the beam into 1, 2, 3 segments. For each segment, you will make a cut anywhere in between at a generic X location. Now your X could be defined from the left end of the beam, or from the right end of the beam, or from somewhere in between, from a division point, for example, as well. Okay, so you make a cut at a generic X location, and then you draw a free body diagram of either the entire left portion from the cut or the entire right portion of the cut. Then you use equations of equilibrium to obtain V and M on the cut section as functions of X. Then once you have the functions obtained, you could draw that, you could plot them basically. So in this specific load case, we would have three different sets of equations. Each set has V of X and M of X. So the first set applies to this little segment of the beam, the second set applies to this little segment of the beam, and the third set applies to the last segment of the beam. Okay. So that's using method of sections. If you choose to use a graphical method, then basically these are the two important relationships. D shear force as a function of X dx, that equals distributed load, and the internal bending moment as a function of X dx, that equals the shear force distribution. In this case, W is considered to be positive if it is pointing upward. Otherwise, in this case, which is downward, W is negative. Okay. So these two relationships tell us how V and M should vary when you look at the load and the shear force. For example, this distributed load gives the slope of V, and V gives the slope of M, and therefore V is always one order higher than W, and M is always one order higher than V. So based on that, you could sketch V and M for different segments on the beam. So when there is a distributed load which is linear, then V should be quadratic, M should be cubic. When this is uniformly distributed, constant, that means V should be linear, M should be quadratic. Otherwise, for a segment where you do not have a distributed load applied, then V should be constant, so a horizontal line segment, and M should be linear. So you should first look at the shape of each segment of the diagram, then you could integrate each of these two, to find M and V at specific points along the beam. Okay. Finally, there will be jumps when you apply a point load or a bending moment. Wherever there is a point load applied, V shows a jump in the direction of the point load. The amount of jump equals the magnitude of the load. But it doesn't create a jump on the M diagram. It would create a turning point, but not a discontinuity. Whenever there is an applied bending moment, then the M diagram shows a jump. If the bending moment is clockwise, then the jump is upward, and when it is counterclockwise, then the jump is downward. Again, the amount of the jump equals the magnitude of the applied bending moment. So that's internal loadings for these three cases. Next, let's take a look at the stresses and stress distribution on cross-sections of these different cases. For extra-loaded members on cross-sections, we have normal stresses, and the distribution is uniform, meaning on any specific cross-section, all the points experience exactly the same normal stress, which is defined as N over the cross-sectional area. If you look at other sections within a axial loaded member, then you'd have to obtain the normal force and the shear force, and there will be a normal stress and a shear stress in general. Okay. So that's stress for axial loaded members, that is uniformly distributed on cross sections. When your N is different from segment to segment, then your stresses are also different on cross sections within each segment, because stress is directly related to the normal force N. Don't directly use the applied loads as your N. N is an internal normal force that needs to be obtained from method of sections. Okay. And the sign of sigma comes from the sign of N. Again, positive is pulling the cross-section, negative is pushing it. So we have either tensile stress or compressive stress. Now for torque-loaded members, the stress is a shear stress on cross-sections of the members. The shear stress is linearly related to the shear stress is linear with respect to the center of the cross-section of a torque-loaded member. So in this course, we focus on circular cross-sections only for torsion problems. So rho is defined to be the radial distance from the center of a cross-section to any point of interest. Okay. So if your point is right at the center, then rho is 0, therefore there is no shear stress at that point. As you move away from the center along a radial line, the shear stress will increase linearly with respect to this distance. So the shear stress on a cross-section reaches maximum when your rho becomes a maximum. That is, when your point falls on the outer surface of the cross-section. And in that case, we say that we have a maximum shear stress on that cross-section, which is Tc over J, where C is a maximum radial distance you could have from the center to a point on the cross-section. And in this case, that would be the radius of the cross-section. Okay, that's why we have a linear distribution. In this case, again, T is an internal torque, which should be obtained using method of sections. And for different segment of the shaft, your T might be different. So the shear stress would also be different from cross-section to cross-section. And J is a geometric property, that is the polar moment of inertia. It is calculated as pi over 2 times radius to the force for a solid bar, and for a hollow bar, it is pi over 2 outer radius to the force minus inner radius to the force. Again, C is radius, not diameter. Okay, so this is J. And for a hollow bar, the maximum shear stress also occurs on the outer surface. Therefore, when you use this formula, tau maximum, your C is just the outer radius of the bar. Okay, that's, again, where you have the maximum radial distance from the center to any point that occurs on the outer surface. Therefore, maximum rho for a hollow bar is also just the outer radius. So that's the stress for torque-loaded members. Now, it's not very clear sometimes of where exactly the maximum shear stress would occur along the length of the member, because that depends on T, C, and J. Okay, all the three could contribute to having a maximum shear stress. So sometimes you'd have to check which section has a larger T and which section has a larger C over J ratio. So the combination would give you the maximum for the entire bar. All right, so that's for torque-loaded members. Now for beams, we have what we call the flexure formula. For this course, we only consider the stress due to the internal bending moment M. The shear force, the internal shear force would cause what we call the transverse shear stress, but that is not discussed in this course. So the stress created by this internal bending moment M is a normal stress, which is normal to any beam cross-section. And it is calculated using negative my over I. This distribution is also linear with respect to not the center anymore, but an axis, which is called the neutral axis. For any beam cross-section, we have a neutral axis. So the line segment along the neutral axis is neither compressed or stretched. So the neutral axis passes through the centroid of the beam cross-section, of any given beam cross-section. So y is defined to be 0 on the neutral axis, and it is going up. So this normal stress can be positive or negative. That would tell us if the fiber or any specific point on a cross-section is in tension or in compression. So the sign of sigma depends on the negative sign of the formula itself, the sign of m, which could be positive or negative, and the sign of y. For any points that are above the neutral axis would have a positive y, because this is how y is defined. And any points on the cross-section that are below the neutral axis would have a negative y coordinate. I is the second moment of inertia for the cross-section with respect to the neutral axis. I won't go over how I is calculated because that has been covered in 212, and we also spent quite some time discussing that. In some cases, you might need to break up a composite area into sub-areas and do an algebraic sum of I. And in some other cases, you might need to apply the parallel axis theorem. So please just review your notes for that part. Now the maximum bending stress on a cross-section, on a specific cross-section, occurs when your y reaches a maximum. Because on a specific cross-section, I does not change from points to points. M does not change from points to points. Therefore, the only thing that changes is y. And y, when y is a maximum, that's either the top or the bottom. Okay, depending on which distance is larger. And we're talking about a vertical distance. We call that distance a c. So again, when we're looking for a maximum tensile stress or a maximum compressive stress, then you'd have to consider the sign of the formula, sign of m, and sign of y. Say that on this cross-section, your m is positive. Therefore, these two would give you a negative sign already. So when y is negative, that would make the whole thing positive. Therefore, the maximum tensile stress in this case, if m is positive on this cross-section, would occur on the bottom surface, where y is a negative maximum value. On the other hand, the maximum compressive bending stress on this specific cross-section would occur on the top surface, where y is a positive maximum value. Now, when we need to find the maximum bending stress across the entire beam, then again, it's really a combination of m and this product, m times the ratio of c over I. So wherever you have the maximum product, that's where you're going to have the maximum bending moment. If the bending moment has the same sign everywhere, so it's positive everywhere, then you just need to look at the specific cross-section that has the largest m. Then the maximum bending stress will definitely occur on that specific cross-section. But sometimes, if the m could show a maximum positive and a maximum minimum, and the beam cross-section is asymmetric with respect to the neutral axis, then you'd have to check both cross-sections to see whichever gives you a combination of this product that is a maximum. So that's the beam stress. Again, it's linear with respect to the neutral axis. Next, let's talk about deflection. So let me just go back to this area. So deflections are quantifying how the members would deform due to the internal loadings. Now, for axial loaded members, we look at the change of length for either the entire bar, which is calculated as NL over EA. N is the internal normal force, L is the length of the bar, E, Young's modulus of the material, A is the cross-sectional area. Now, this is used only for the following case, which is you have the axial loads applied at both ends of the bar. When this is not the case, we could either do a sum, we might have multiple terms, or we could do an integration across the length of the bar. Okay. Now the bottom formula is used when the cross-section of the bar changes as a continuous function along the length, or the internal load on cross-sections varies as a continuous function of x, or the material property varies as a continuous function of x. Now this is used when you have an abrupt change of the cross-section, material, and or when you have some other axial loads applied somewhere along the member. Okay. So whenever you have an abrupt change in material in cross-section, or when you have a load applied, then that would be your division point. So when you divide the bar into a few segments, in this case we need 1, 2, 3, 4, 5 segments. That would give you 5 terms in this algebraic sum expression. So each term represents the relative change of length of one end of the segment relative to the other end. It could be positive or negative. The sign is determined by the sign of n. Again, that comes from method of sections. Now L for each term is the length of each segment of the bar. So for the first segment, L is this length. For the second segment, L is this length. Third is this, etc. E is the material property of the material for that segment, and A is a cross-sectional area for that segment. So that's how deflections are calculated for axial loaded members. Now I want to point out that sometimes there could be a temperature change as well, and when that is the case, for each segment of the member, the delta deflection is the algebraic sum of a mechanical deformation and a thermal expansion. The mechanical deformation is calculated using NL over EA, as I have described earlier, but the temperature thermal expansion is calculated as alpha delta T times L, and again L is the length of that segment, delta T is the temperature change of that segment, and alpha is a material property. It's the linear coefficient of thermal expansion. So delta T could be positive or negative, which will make this delta T positive or negative. If the temperature is increasing, we have a temperature increase, then delta T is positive. Otherwise, when delta T is negative, we have a temperature decrease. That would cause the segment of the bar to contract due to the temperature effect only. The net effect for each segment could either be elongation or contraction. Again, it depends on which term has a stronger effect if their signs are opposite to each other. So this is for axially loaded members. For torque-loaded members, the deflection we consider is the angle of twist or rotation of a specific cross-section. So we have phi, which is an angle in radians. That is defined to be TL over GJ. Now these two are really analogous to each other. We have an internal load, T, N, length, L, material property, GE, geometric property, J, and A. All right, this is used when you have just the torques applied at the very ends of the bar, then you have one term. This could be positive or negative. Again, the sign comes from the internal load T. The internal load should be determined from method of sections. When you do need to divide the bar up into a few segments, then you can have a few terms. Again, this would become an algebraic sum. Each term represents the rotation of one end of that segment relative to the other end of the segment. So it's a relative measure. You could also do an integration when the material property, cross-section, and or the internal torque changes as a continuous function of x along the length of the member, then you do the integration. Otherwise, we have this algebraic sum. So your division points are again where you have an abrupt change of cross-section, an abrupt change of material, and or when you have a torque applied somewhere. So in this case, we need to divide the bar into 1, 2, 3, 4 segments, and this one would have 4 terms. Now, L, again, is the length of that entire segment. So for the first segment, L is this length. Okay. So when you use this, you need to be a little careful with J. Again, it's calculated differently for a solid cross-section versus a hollow cross-section, a tube. And another thing that I want to point out is that when you want to find the absolute rotation of an end, then you always refer everything back to a wall, say, or any point that has 0 rotation. So, for example, if we have a point B, A, and C, where A is fixed to a wall, when it is fixed, that means it has 0 rotation. So no rotation is allowed when it is fixed. So if we want to find out the rotation of end C, for example, then that's an absolute quantity. So we use C relative to B and B relative to A if there is a torque applied or something such that B is a division point, then you divide the entire bar into 2 segments or something. So these relative measures plus the absolute rotation of the other end. Okay. In this special case, A is fixed to the wall, therefore you have 0 rotation there, and phi A is 0, so phi C just happens to be the sum of the algebraic sum of the 2 relative measures. So that's torque-related measures. Finally, for beams, the deflections are a vertical displacement or a slope of the elastic curve. So beams could deflect downward and or upward due to the loadings. So we are looking at the vertical displacement V as a function of x. So at any specific point, V could be positive or negative, so it's a vertical displacement. So if the beam deflects upward, V is positive, otherwise it's negative. Now, slope of this curve is what we call theta. It could also vary as a function of x along the length of the beam. So theta is slope of the elastic curve, so d little v dx. So that's a deflection. Now we've introduced 2 different approaches to find the beam deflection and or slope. So we've introduced the method of integration. We also have introduced the method of superposition. Now these are more recent topics, so I won't go into details. Just want to quickly remind you that for method of integration, you can either start with the 4th order differential equation of V that equals the distributed load W, which is positive when the load is upward, negative when it is downward. Or you could start with the 2nd order differential equation, but I'm going to write down all of them. The 3rd order differential equation is in terms of the internal shear force V, and the 2nd order differential equation is in terms of internal bending moment M. And if you integrate this once, you get slope that equals the integral of M. So that's EI times slope. Now this is assuming that EI is constant everywhere along the beam. If that is not the case, if these are continuous functions of x, then you need to include them inside of the derivatives. Or if I changes or E changes, then you have to do this for different segments of the beam such that within each segment you have constant EI. Alright, so again, we in general either start with the 4th order differential equation or the 2nd order differential equation. We use the 4th order differential equation when the distributed load is quite complicated, like a sine function, a quadratic function, etc. Otherwise, we always start with the 2nd order differential equation. And we apply this to different segments of the beam. And the way the beam is divided into segments has been discussed earlier. So whenever you have an applied point load, applied bending moment, or your distributed load starts to apply or it ends somewhere, those are division points. So this should be this should be written for each segment, and then you will need to integrate this twice. So M is the internal bending moment for each segment, and we've already discussed how this is obtained when we were looking at internal loadings. So after you integrate this twice or this 4 times, you would end up having some integration constants. Now those constants can be obtained by using boundary conditions, symmetry, as well as continuity conditions. So for boundary conditions, we have, if there is a wall, then at the wall location, deflection of the beam is 0, slope of the beam elastic curve is also 0. When you have a pin or a ruler that's connecting the beam to ground at locations like these, you again have 0 deflection because the beam is not allowed to move in a vertical direction when there is a pin or a ruler. So those are boundary conditions. Now for continuity conditions, then if you have a division point somewhere, then you'd have to have 2 different second-order differential equations, one for the first segment and one for the second segment. You would integrate those second-order differential equations twice. So you have 2 sets of integrations, and at this point, the deflection curve should be continuous. Therefore, the deflection of the curve determined from the first segment using the first second-order differential equation, the integration of the first second-order differential equation should match the deflection obtained from the second segment of the curve, and the slope is the same. So those are continuity conditions. So for method of superposition, the basic idea is that you can, when there are multiple loads applied to the beam, you can apply one load at a time, and the total deflection and total slope could be the algebraic sum of the deflection due to each load applied on the beam only. And you can use appendix C to find deflection and slope information. Okay, looks like we're having 2 minutes. The battery is running out. But very quickly, the last thing we talked about are statically indeterminate problems for all these 3 types. Now, when the problem is statically indeterminate, you have more unknowns for reactions than the number of equilibrium equations that you have. Therefore, you cannot solve for all of them using equations of equilibrium. You're going to need compatibility equations on top of equilibrium equations. So the compatibility equations are usually in terms of the deflections of the members, and you'd have to draw. Sometimes it's very easy to identify the compatibility equation or equations. Other times, you will need to draw load displacement diagram and look at how things deform under the loads applied, and therefore find some geometric relationships. Okay, but those are usually in terms of the deflections. For beams, it could also be in terms of the slopes. Then the strategy is to write the compatibility equation in terms of the unknown support reactions. So the compatibility equations would provide additional equations in terms of the unknown support reactions. That's how you could determine all of the unknown support reactions. All right, since the battery is running out, I guess I will conclude right there. So that's a summary of all the topics we have introduced. Thank you.